Solubility equilibria are going to be the topic in the last lesson here in our chapter on chemical equilibrium. And we're going to deal with a new special type of equilibrium constant that we're going to call KSP, which will be the equilibrium constant for when an ionic solid dissociates in water to form its aqueous ions. And we're going to do all the associated equilibrium calculations that go with it. Now, this lesson is part of my high school chemistry playlist. I'm releasing these lessons weekly throughout the school year. So if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. All right, so let's dive into this here. So solubility equilibria. So solubility, we dealt with some solubility rules earlier in the course and stuff like that, and we had solubility rules for ionic compounds in water. And that's what we're going to be dealing with specifically in this chapter. So a KSP is our new special equilibrium constant, and you're always going to have an ionic solid as a reactant, and you're always going to have aqueous ions that it dissociates into as products. So we're going to take a look at three different KSP reactions and their corresponding expressions. And first one here is going to be for silver chloride here, AgCl. And the KSP reaction, you're always going to have the ionic solid as a reactant, and then it's going to dissociate to form its corresponding aqueous ions. And when AgCl dissociates, you get a single silver ion and a single chloride ion. So, and in this case, your KSP expression would just be Ag plus times Cl minus all over 1. In this case, your only reactant is a solid. And again, no solids and liquids typically showing up in our equilibrium constant expressions. And so in this case, if all your reactants aren't going to show up, then it's just over 1. And anything over 1 is just itself. And so that's why this looks this way. And this KSP, the SP again stands for solubility product. And product here refers to multiplication, because this is just going to be the multiplication of a couple of ion concentrations, because your reactant's always a solid when you have a KSP. And so you never have a denominator in your expression here. So that's for AgCl. Let's take a look at what it looks like for MgOH2 here, magnesium hydroxide. So again, your reactant's a solid. It's going to dissociate to give this time a single magnesium ion and then 2 hydroxide ions. Notice that, we say that it's always for an ionic solid dissociating in water for these KSPs, but notice water doesn't actually show up in the equation at all, but you can infer that it's there because we have aqueous ions as products. It's all dissolved in water. All right, so our KSP expression for this one, Mg2 plus times hydroxide squared. So again, products over reactants raised to the power of the coefficients. Well, in this case, our reactants are always going to be a solid, so you're never going to see a denominator, but we still have to factor in those coefficients as exponents here. All right, finally for bismuth iodide here, same kind of thing. Dissociates to give a single bismuth ion. And then 3 iodide ions as well. See if I can fit that aqueous ion in there. And once again, your KSP is going to equal products Bi3 plus times I minus cubed. Cool, so that's the first part. You might have to come up with either the reaction that KSP is the equilibrium constant for, or you may be asked to come up with the actual KSP expression for any, the solubility of any ionic compound. So here we've done it for 3. That's the first kind of question you could get. Now we're going to talk about the calculations associated, and this is where students often get really tripped up. But again, in principle, this is no different than everything we've seen. So it'll have some common patterns that develop, and students often get stuck in these patterns. But if you treat this just as any other equilibrium calculation, it'll come out and work out the same. I highly like some of the patterns you can come up with, but I think you should learn those patterns after you just kind of treat this the way you would any other equilibrium problem. So let's take a look. First question on your handout is, what is the molar solubility of AgCl? Okay, and then a KSP is given of 1.8 times 10 to the negative 10. Let's fill in our ice chart first before we talk about what the molar solubility is. And so in this case, if we fill in an ice chart, so this is going to get a little bit tricky. But if we start with just plain old AgCl solid and we put a pinch of it in water, well, before it dissociates, there really shouldn't be any silver ions or chloride ions in that water. And that's why these are going to be put in as zeros here initially. So I'm not going to worry about initial concentration of a solid, because solids, again, don't really have a concentration in the same way that something that's aqueous does. So, but then we'll deal with the change. And in this case, we'd say like maybe minus x here and plus x here and plus x here. And here's the deal. We don't typically fill in the chart for solids or liquids. So why am I filling it in here? Well, it turns out that x here is the concentration of the solid that dissolves. And so that is actually what we term the molar solubility. It is the molar concentration of solid that dissolves. And if you fill out your ice charts in exactly the same way we've been doing them the whole time, x by definition in the ice chart is the molar solubility. So here, x equals what we call your molar solubility, or simply the solubility in units of concentration, in units of molarity. All right, so oftentimes because of this, a lot of textbooks and instructors will get to this section, and instead of using x, all of a sudden they'll start using s's. And they'll say, oh, no, let's put an s in there instead. So, and because S stands for solubility. So, and they want students to get the point that S in the ice chart is solubility. Well, I don't like the inconsistency personally, and I'm just going to keep using X's. So, but just so you've seen it in case you're taking this in high school and your instructor's doing it the other way around, great. And again, technically we don't usually show the changes or any of the stuff for a solid, so I'm going to leave that out, but we'll have plus x, and 0 plus x is x, and 0 plus x is x. And so now I'd have the equilibrium concentrations, but the key is though, is that if they're asking you for the molar solubility, they're asking you to solve for x from the ice chart. Okay, so in this case, we can see the KSP is given as 1.8 times 10 to the negative 10, and that's going to equal x times x, or simply x squared. And so from here, all we do is take the square root, and we're good to go. So we'll pull out our trusty calculator. It should be 1 point something other times 10 to the negative 5. So square root of 1.8 times 10 to the negative 10 is 1.34. So I'll round it to 1.3 times 10 to the negative 5. And that's in units of molarity. Cool. So if you put AgCl in water, it's not going to dissociate to any significant extent. It's only to a small extent. And we'll give you a KSP that corresponds to this. And notice that KSP is really tiny, 10 to the negative 10. Again, that's a reaction that heavily favors the reactants at equilibrium. And so in this case, we're not going to form very much of the products based on these KSP values. And so typically we're going to give you KSPs for things that are fairly sparingly soluble, very low in solubility. And so you're typically not going to have very large molar solubilities. And that's not the biggest number in the world. Now, if you put a pinch of AgCl in water, so the max amount that can dissociate, it's not going to be very high. And so what you'd find is even putting a pinch in water, you're probably going to still see some AgCl grains sitting on the bottom of your beaker. So when that happens, when you still have some solid left over sitting on the bottom of your beaker, that's evidence that you have what we call a saturated solution. We saw this several chapters back towards the beginning of the course. We use that word saturated. That just means the maximum amount that could dissolve has dissolved. And so we typically use these KSPs for these saturated solutions. So you might see, what is molar solubility? Or they might ask, what is the silver ion concentration in a saturated solution of AgCl? Or what is the chloride ion concentration in a saturated solution of AgCl? And that's cluing you in that just, well, how much is present at equilibrium? And so in this case, it actually would just equal x as well. And so if I said, instead of saying what's the molar solubility, which was again 1.3 times 10 to the minus 5 molar, if I said what's the silver ion concentration in a saturated solution of AgCl, you'd just give the same answer, 1.3 times 10 to the negative 5 molar. What's the chloride ion concentration in a saturated solution of AgCl? Still just 1.3 times 10 to the negative 5 molar. Cool. So just wanted to be prepared to see it either way. Let's move on to the next one here. So for magnesium hydroxide, the question is, what is the molar solubility of magnesium hydroxide? And once again, you're given a KSP of, what is it? 1.6 times 10 to the negative 12. So there's your KSP. And in this case, it's going to equal the magnesium concentration times the hydroxide concentration squared. And so in this case, if we filled in an ice chart here, once again, we have 0, 0, plus x, but notice it's a 1 to 2 ratio, so this is not plus x, but it's plus 2x. 0 plus x is x, 0 plus 2x is 2x, and now we can plug those equilibrium concentrations right into our expression. And so the concentration of magnesium at equilibrium is x, right off the ice chart. And the concentration of hydroxide at equilibrium is the 2x, right off the ice chart. And here's where things get confusing. Notice there's a 2 for the formula as an exponent, but when you substitute the terms of x in there, the 2 shows up again in terms of 2x. And that often gets a little confusing. So sometimes try to draw the 2 like right here next to a chemical symbol. It doesn't work that way. It can be next to the x, but there's no 2 that goes right there when you're writing the expression, so be careful with that. Sometimes when writing the expression, they like to throw examples where they put 2's inside the brackets next to hydroxide or something, just to try and trip students up and give a good detractor answer that's wrong, but don't fall for it. All right, so if we look at this, then 2x, when you square it, not only are you squaring the x, you got to remember to square the 2, super common error. And so this doesn't equal 2x squared, it equals 4x squared when you square it. And then when you multiply by another x, you get 4x cubed. So and before you solve this, you're going to have to divide the 4 out first. So in this case, if we take 1.6 times 10 to the negative 12 divided by 4, we're going to get 4 times 10 to the negative 13. And then we'll take the cubed root. And in this case, there is a special way to do the cube root on your calculator. So, but I don't use that. It's, you know, you've got through some menus and stuff usually to find it. And so what I usually do is take a caret symbol and in parentheses put the 1/3, 1/3 power. Because a 1/3 power is the same thing as a cube root. And in this case, we're going to get 7.4 times 10 to the negative 5. That's in units of molarity again. So again, here we took a cubed root, which is the same thing. And again, I really just took 4 times 10 to the negative 13, caret to the 1/3 power. That's what I put in my calculator right there. Cool, so that comes out to 7.4 times 10 to the negative 5 molar. And again, that's x. That is the molar solubility. This is the question we were asked. Now, had the question been, what's the concentration of magnesium ions in a saturated solution of magnesium hydroxide? Well, I'd have to look on my ice chart and be like, oh, it's equal to x. And it would still be 7.4 times 10 to the negative 5 molar. But if the question is, what is the hydroxide concentration in a saturated solution of magnesium hydroxide? I look at my ice chart, and it's not equal to x. It's equal to double that value. And so I'd have to take that 7.4 times 10 to the negative 5 and double it. So to answer the hydroxide concentration. Cool, so that's the first two. We've done solubility, we've done calculating the molar solubility. The next one's going to be the exact opposite. Instead of being, given KSP and asked to solve for x, the molar solubility. And the third one here, we're going to be given the molar solubility, given x, and asked to solve for the KSP. So the last one here says the molar solubility of bismuth 3 iodide, BiI3, is 1.32 times 10 to the negative 5. Calculate KSP. So now we want to calculate KSP, but they're telling us that x equals 1.32 times 10 to the negative 5 molar. So that's our x. That's what's being given. A lot of students don't realize when we're told that the molar solubility is something that they're actually telling us x. So KSP is called the solubility product constant. So x here from the ice chart is called the molar solubility. They both contain the word solubility, and that sometimes trips people up. So keep that there. And if we look at our ice chart again, so we'll have 0, 0, plus x, plus 3x. 0 plus x is x. 0 plus 3x is 3x. And so if we substitute these in, we'd substitute an x in right there, and then we'd substitute a 3x in right there, and then have to cube it according to the formula. And so in this case, 3x quantity cubed, again, not only are you cubing the x, you got to cube the 3. And 3 cubed is 3 times 3 times 3, which is 27. And 27x cubed times another x is 27x to the 4th. And that's going to equal our KSP value that we're trying to solve for. Cool. And so the key is they gave us x, and so we're just going to substitute it in right there. And so in this case, we're going to have 27 times 1.32 times 10 to the negative 5 to the 4th power. And now we can solve for our KSP. Let's give ourselves a little bit of room here. Okay, so in this case, I'll take the 1.32 times 10 to the negative 5 raised to the 4th power. And then I'll multiply that all times 27. In this case, I get 8.2 times 10 to the negative 19. Cool. And there indeed is our correct answer. All right, so now we've been given two types of problems here. We've been given the KSP and asked to solve for the molar solubility, like in the first two, or we've been given the molar solubility X and asked to solve for the KSP. Now we've got one more type of question that I'm going to call the common ion effect. It'll be related back to this first one, so let's take a look. All right, so this last equilibrium calculation here says, what is the molar solubility of AgCl, but in 0.1 molar HCl? And we're still given the KSP is 1.8 times 10 to the minus 10, just like we were given back in the original problem. So this first one we dealt with in this chapter was, what is the molar solubility of AgCl, period. Okay, and we learned how to deal with that. But now we're given, what is the molar solubility of AgCl in 0.1 molar HCl? And so the way this works, we often get the solubility of something, and they're going to give you a strong electrolyte. Notice HCl is a strong acid, a type of strong electrolyte, so it's going to dissociate completely in water. And they're going to give you something that's a strong electrolyte that has something in common with your salt of interest here, your ionic compound of interest. And in this case, what they have in common is the chloride. And so we call that a common ion to these two substances. And so this is what's called the common ion effect. And so because HCl dissociates completely to produce a bunch of chloride, I mean, it also produces a bunch of H+, but I don't really care about that. I care about what's in common here, but it's going to put a bunch of chloride in the solution. And if you look, if we put a bunch of chloride in the solution, that's adding a product here. And according to Mr. Le Chatelier, that's going to shift this equilibrium back to the left. And if we shift this equilibrium back to the left, that means we're going to have less AgCl that actually is dissolved. And so this actually lowers the solubility. And so in this case, the common ion effect, if you add any strong electrolyte that contains either silver or chloride here, it lowers the solubility of AgCl, it turns out. And so we're going to see that when we calculate the molar solubility now, that it's no longer going to equal 1.3 times 10 to the minus 5. We should expect it to be considerably less, as we'll see. All right, so normally what we do is a lot of people get used to the pattern on the ice chart, and they're just like, yeah, make that x, and set it equal to KSP, and you get 1.8 times 10 to the negative 10, and they say times x and times x. Well, again, that's when you don't have a common ion present. If you have a common ion present, it works just a little bit different. And so we're going to set up our ice table here, and we're still going to have plus x plus x. The key is normally we'd set this up and we'd set both of these equal to 0, and we'd say before AgCl dissociates, how much silver and chloride should be in our solution? Well, before AgCl associates, if it's pure water, then none. But we don't have pure water. We have 0.1 molar HCl, and 0.1 molar HCl dissociates to give you 0.1 molar H plus and 0.1 molar Cl minus, and that's what I care about. Before my AgCl even dissociates, there's not 0 amount of chloride, there's 0.1 molar. And so that's where this changes the math here on the setup, is we already have chloride in our solution, a lot of it, before AgCl even dissociates. And so before the dissociation, our initial concentration of chloride is not 0, it's 0.1. That's the difference. And so in this case, 0 plus x is still x, and 0.1 plus x is not just x, it's 0.1 plus x. And so now we can go substitute our equilibrium values into our KSP expression, and we're going to have x times 0.1 plus x. And now we got to solve for x to get our molar solubility. So x is still equal to molar solubility, even in a common ion problem, because that's the concentration of the solid that would have been dissolving. So it's still equal to x, our molar solubility. So that's what we're still solving for here. But now we got a problem. If you want to solve for x here, you got a quadratic. If you distribute the x through, you have 0.1x plus x squared, and you could get all the terms on one side and solve a quadratic equation, and life would suck. Except we're not doing quadratic equations. And for good reason. This equilibrium constant is tiny. And if this equilibrium constant is tiny, this reaction favors the reactants heavily, which means the amount of solid that's going to dissociate is going to be tiny. We're not going to form a lot of these products. So we should expect x to be small when your equilibrium constant is small. And if x is small, then you can ignore it if it's added or subtracted to or from a much larger number, like it is right here. 0.1 plus a really tiny number, for all practical purposes, is 0.1. Now you can't ignore it when you're multiplying it, because when you multiply by a small number, it has a huge impact. But when you add or subtract a small number to a much larger number, just ignore the x. And so in this case, this reduces down So 1.8 times 10 to the negative 10 equals x times 0.1. We'll divide both sides by 0.1 to get x equals 1.8 times 10 to the negative 9 molar. Cool. And that is x, which is our molar solubility, what we're being asked here. And so in this case, the molar solubility of AgCl, period, which means just in pure water, is 1.3 times 10 to the negative 5 molar. But we just found out the molar solubility in 0.1 molar HCl is 1.8 times 10 to the negative 9 molar. That's roughly 10,000 times lower in solubility. So huge decrease in solubility due to the presence of a common ion, chloride in this case. And that's how we'd work the calculation here. All right, so now we want to conclude this lesson by making a big conclusion. That'll help you with calculations in the future, but also going to allow us to make some conceptual comparisons that are not really going to be math related to any significant extent. So I want to talk about like when you have two ions, if you're solving for the molar solubility when there's no common ion present, which will be the most common kind of question you get in this section. So we can make some generalizations. So if your ionic salt dissociates into just two ions like AgCl does, ultimately, when you set up your ice chart and everything, you're going to get KSP equals x squared. And so if you had to solve for the molar solubility, you'd just be taking the square root of the KSP value. Now, if you've got it dissolving into three ions, like one magnesium and two hydroxides, like we saw with magnesium hydroxide, what you'll find is that you can make a determination that KSP is going to equal 4x cubed. And the way this works, you can look and say, I'm going to get one magnesium, so that's 1x to the 1 power is the way it works. And then I'm going to get two hydroxides, so that's 2x to the 2 power. That's kind of what the result of our ice chart was and stuff like this. And work that out, that comes out to 4x cubed. Same thing like if it dissociates into four ions like BiI3, one bismuth, three iodides. And in this case, your KSP comes out to 27x to the 4th. And the way you might derive that is you could say that KSP equals 1x to the 1 power, since we get one bismuth ion, but because we get three iodides, it's going to be times 3x to the 3 power. And if you work that out, lo and behold, that's where you get the 27x to the 4th. And so this is what I said earlier when I said, you know, a lot of you are going to memorize some patterns for these calculations before you ever set up an ice chart. And I wanted you to, you know, work these out with an ice chart. But at the end, as long as you're just doing molar solubility and there's no common ion present, this is what it reduces down to. But this also allows them to ask you another type of question, and this is more conceptual. They might give you 3 salts or 4 salts or something like this, give you their KSPs, and just say which of these has the highest solubility or lowest solubility. Might do it either way. So I'm going to say which of these has the highest solubility. Well, again, the highest solubility means the highest molar solubility, which means not necessarily the highest KSP value, but the highest value for X from the ice chart. Well, if you notice, all of these dissociate into two ions, one silver, one chloride, one silver, one bromide, one silver, one iodide. And if all of them dissolve into two ions, then this is ultimately the expression you'd get. And when you go to solve for X, it would simply equal the square root of KSP. And so in this case then, if you want the one that's going to get the highest X value, well, that ends up going to be the same one as the one with the highest KSP value. And if you've kind of memorized this kind of relationship, you just look at these and be like, oh yeah, higher KSP means greater solubility, as long as they all dissociate into the same number of ions, it turns out is the key though. But in this case, you just look at this and be like, yep, 1.8 times 10 minus 10 is the largest of these three numbers, so AgCl has the highest solubility. Okay. Now, the tricky part gets to be, what if instead I throw an extra salt on here, like we throw that magnesium hydroxide on there, which was the 1.6 times 10 to the negative 12, and there you get a problem. Because this dissociates into three ions, we ended up with KSP equals 4x cubed. If you go to solve for X on this one, well, the first thing you'd have to do is divide your KSP by 4, and then you'd have to take the cube root. And all of a sudden now, like comparing something where I'm just taking the square root of KSP to get X versus something else where I'm taking the cube root of KSP over 4, I can't just compare their KSP values anymore. It doesn't work that way. And I might actually have to do a calculation. Now, the good news is this. You are way less likely to see something that would include salts that dissolve into different numbers of ions on a question like this. Most likely, they're just going to give you 3 or 4 salts that all dissociate into the same number of ions, and in that case, you could just use the KSP value as your base of comparison. If that's the case, highest KSP is most soluble, lowest KSP would be least soluble, and life would be good. It's only if they include an additional example that dissolves into a different number of ions that you might actually have to do a calculation. Now, if you found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can do to make sure that other students get to see this lesson as well. If you are looking for the study guide that goes with this lesson, if you are looking for practice problems involving equilibria, check out my premium course on chadsprep.com.